Okay, now we get to the, hold on a sec, let me, there we go. We get to the big one, the ratio test. There are more tests that we're going to do, but this is one that you really want to key in on. It may or may not be referred to by name on the exam, but I guarantee you're going to have to do the ratio test at one point. The reason being is that it's a very powerful test, and it's actually one in which you can work your way through it. I think you'll actually like this test. Basically, the idea is that we're going to find the ratio, kind of like what we did with geometric series a long time ago. Okay, we're going to find the ratio of one term to the next, from the nth term to the n plus 1th term. N plus 1th term? That sounds about right. Okay, we're going to compare the two terms and look at the ratio. Okay, if the ratio of the n plus 1 term to the nth term is less than 1, the ratio test tells us that the series will converge. Okay, just like with the geometric. Okay, if the ratio of as one to the other is greater than 1, then we will diverge, and then if it's equal to 1, then the test is inconclusive. We've heard that word before. Yeah, the test just does not work. So what we're looking to do is take the limit as n approaches infinity of the n plus 1 term over the nth term. We put the absolute value signs in there. That'll help us out later on when we're checking endpoints. So just bear with those absolute value signs for now. Okay, so let's do an example here. We have the series n goes from 1 to infinity. It's 3 to the n over n times 2 to the n, and the question is whether or not this series converges. Okay, so we're going to set this up. Okay, if you're writing notes down, don't write this first thing down that I'm about to do because I want to show it to you in a slightly different way. Okay, so what we have here is we have the limit as n approaches infinity. All right, and then we have a huge fraction inside of an absolute value. Okay, so what ends up happening is because the series is rational, we have 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. That's the numerator of our large fraction. That's the n plus 1th term. And then we have the original series in the denominator, 3 to the n over n 2 to the n. Okay, and then this is all inside absolute value. All right, that's pretty confusing. Again, we have fractions inside of fractions. I don't think you want to go this way, okay? But you learned a whole long time ago about the whole keep, flip, change thing when we're doing a fraction divided by another fraction. And basically what we're allowed to do is just multiply the two as long as we reciprocate the denominator. That's the better way to set this up. So what I'm looking for you to do really is to go limit as n approaches infinity. Okay, absolute value. We're going to do our n plus 1 term. So we have 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. And instead of dividing it by the nth term, we're going to multiply it by the reciprocal. Okay, so we'll have n 2 to the n over here and 3 to the n right there. And now that's a much nicer way of looking at things. Okay. So let's see if I can fit this in. I'm actually going to go up here just to give myself a little more room. We now need to simplify this because we need to take the limit as n approaches infinity. I'm not really in the mood to plug infinity into this right now and figure out what's going on. Let's make it look nicer. Okay, how can we do that? Well, we see up here we have 3 to the n plus 1. So it would be cool if we could cross out the 3 to the n plus 1, but we need the 3 to the n plus 1 down here. We don't have that, okay? Or do we? All right, let's go look at 3 to the n plus 1, okay? That's our exponent rules, 3 to the n plus 1, okay? That's equal, by the definition of our exponents, that's equal to 3 to the n times 3 to the first, right? Because if I didn't have this up on the board and I said, what's 3 to the n times 3 to the first, you would add the exponents. You have the same base, different exponents, you're looking for the product of the two, so you add the exponents. There's the first exponent, and we're adding it to the second exponent. So 3 to the n plus 1 is really 3 to the n times 3. Okay, so let's write this down. Limit as n approaches infinity. Okay, here's our first expression before the multiplication. Instead of 3 to the n plus 1, we're going to write 3 to the n and multiply it by 3. Okay, down in the denominator, we still have our n plus 1. But would you agree that 2 to the n plus 1 is just going to be 2 to the n times 2, using the same exponent rule as up there. Okay? Now, that's good for us, because now if we write down the second one, we don't really have to change the second fraction here, n, 2 to the n, and then 3 to the n. Well, now some stuff starts to happen, doesn't it? All right, cancel some stuff out for me, please. Okay, I'm guessing that you crossed out the 3 to the n's, and you crossed out the 2 to the n's. Very good. What does that leave us with? Well, in the numerator we have 3n, don't we? 3 times n. So we are looking at the limit as n approaches infinity, and we've got absolute value, we've got 3n in the numerator. In the denominator, well, that's gone and that's gone, so we're left with 2 times the quantity n plus 1. Everybody okay if I just distribute that 2? Okay, so we've got 2n plus 2 down there. And that's it. Everything else canceled out. Well, this is first month of AB. Limit as n approaches infinity of 3n over 2n plus 2. What's that equal to? That's equal to 3 halves. 3 halves, I'm pretty sure that's greater than 1. And if the ratio is greater than 1, the series diverges. So we have just used the ratio test to prove that this series diverges. Okay. Now that's a lot going on there. It just took me 6.5 minutes to go through that, and that's just one example. And there's going to be more examples with ratio tests, and especially there's going to be examples in which we have n and x, and that's going to lead us to finding the interval or radius of convergence. Okay, so that's coming down the pike, but for now we just have the ratio test. We'll hammer out a couple of those, and then I'll get some more videos going as far as doing some more with the ratio test, and then we'll get into the final couple of tests, which involve alternating series, and also I think I need to show you the root test as well. So thanks for your attention today, and we'll see you soon.